Alright, so let's have a look at question 4. Determine the following derivatives. It's not necessary to simplify, but your answers must be given with positive exponents. So let's have a look at the first one. I'm finding the derivative of one function multiplied by another function, which means I'm using product rule. Now, with this question, we did penalize once overall for notation, so you need to be very careful about that dt. That dt is an instruction to differentiate, and it's saying that the actual function has t's in it, so I'm differentiating with respect to t. So let's have a look how that plays out. Once you actually find the derivative, that dt doesn't feature anymore. So remember, using your product rule, you're going to find the derivative of that first function, which is 9t squared minus 8t plus 5. You multiply it by the second function as is, 3 root t minus 1 over t. And then you add that first function as is, 3t cubed minus 4t squared plus 5t. And you multiply it by the derivative of the second function. Now, what is important to remember, and I didn't show it in a step here, but it's very important that you change those so that you've got coefficient base exponent. So in other words, I know that that is 3t to the half minus t to the negative 1. So when I actually go and differentiate, I get 3 times a half, which is 3 over 2. 3 over 2 t, and I subtract 1 from a half, which is negative a half, plus, because that's negative 1 times a minus, t to the negative 2. Now you notice that you still have negative exponents. So I've got to go and just make sure that my final answer does not have negative exponents. You could have gone straight here if you saw it as well. Okay, so let's get right at the end rid of those negative exponents. And it's not required, you don't have to, but t to the negative half, that t to the half goes to the denominator, which is in fact root t. It's just neater when you end it like that. Plus 1 over t squared. Mark allocations for that question. You get a method mark for using the product rule, and then you get accuracy marks for each bracket. So accuracy, 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 and accuracy. Let's have a look at the next one. Alright, in this question you can see that we're using the quotient rule. Again, take note of notation. The d over dp means I'm finding the derivative of this function with respect to p. So the moment you actually find the derivative, then you don't have to write that notation anymore. So I can go straight to finding my derivative here. I start with the derivative of the numerator, which is 4p plus 5, multiplied by the denominator as it stands. Then I subtract the numerator as it stands, multiplied by the derivative of the denominator, which gives me 6p minus 4. Don't forget your denominator in the derivative. That's your original denominator squared. You didn't have to simplify any further. So let's have a look at your mark allocation here. You get an accuracy mark, an accuracy mark, an accuracy mark, and an accuracy mark. Oh, don't forget your method mark for using the quotient rule. Then you don't get a mark for the denominator, but we are penalizing 1 if you forgot your denominator. So if no denominator, you get penalized 1 mark. Let's look at the next one. Alright, so here we've got the derivative of the function with respect to x. And here we're using the chain rule because you should be able to see that there is a function inside a function. So my main function is 3 times something to the power of 4. And the function inside that function is 5x squared minus 2. That's my function inside my function. So let's go and have a look. First, you're going to differentiate that outside function. It's 3 times something to the power of 4. That 4 comes to the front, you get 12 times that something, 5x squared minus 2. And you subtract 1 to get 3. Then you go inside, and we're going to find the derivative of 5x squared minus 2, which is 10x. You don't have to, but you can go one step further, and you can multiply the 12 and the 10x to get 120x, just to make it look a little bit more pretty. So if you did that, that's great, but your marks are as follows. You get 1 method mark for using the chain rule. You get an accuracy mark for your 12, an accuracy mark for that first bracket, and an accuracy mark here. Okay, let's have a look at the last one in question 4. Okay. Alright, so here you get asked to determine the derivative without using a calculator, because I've shown you in class that there's quite an easy shortcut with your calculator. Use that shortcut to check your answer, but this is asked without a calculator to get your 6 marks. So you need to start by finding the derivative of that function. Now we don't like roots when we're finding derivatives, so I'm going to rewrite it without the root. Note that then we've got 4x squared minus 12x to the power of a half. Now I can find the derivative. Again, beware of your notation. This is now f prime x or dash x. This is the chain rule, so that half comes to the front. That function inside is my thing. That's part of my first function. Then I'm going to subtract 1, so I get negative a half. Go inside. And find the derivative of 4x squared minus 12x, which is 8x minus 12. Now I can then go one step further. I don't need to make that look pretty. What I do need to do is I need to sub negative 1 in place of x. So wherever I see my x, I'm going to put a negative 1. So I've got 4 times negative 1 squared minus 12 times negative 1 to the power of negative a half. Then I've got times 8, negative 1 minus 12. It's always good in AP to show that step. You don't need to show any other steps after that. If you plug that all in your calculator, and I think this might be one that was rounded off, you're going to get negative 2 comma 5. Let's have a look at your mark allocations. Okay, firstly you've got accuracy marks. You've got 1 for the half, got 1 here, got 1 here, and you've got 1 here. Then you've got a method mark for your substitution and an accuracy mark. The reason why it's accuracy is because your silver calculator can check it for you, so that you can go back and check that answer. Alright, let's have a look at question 5. Consider the function. You've got a cubic function there. First, you need to determine the intercepts with the axes. So let's start with our y-intercept. With our y-intercept, you make x to be 0. You can see quite easily that your y will be 16, but remember to put it as a full coordinate. Okay, so now let's have a look at our x-intercepts. To find them, we need to make y equal to 0. Now, you can use your calculator as a bit of a shortcut here, because it'll find your solutions for you. But I'm going to go the longer way around, and I'm going to factorize my function. Okay, so let me write it out first so you can see what I'm doing. Make my y 0. I'm going to factorize. You can use your calculator to help you. I'm not going to go in depth about how to factorize at this point. But you get your first bracket, and you get your trinomial. Then by long division, synthetic division, or by inspection, you've got that. Okay, I'm not too worried about the method you used right now. Then I want you to factorize your trinomial. So you can see that you've got x-intercepts, you've got a repeated one, so you know it's eventually going to turn on the axis, and your x-intercepts are 2, 0, and -4, 0. So mark allocations here, you've got a accuracy mark for your y-intercept, and you've got an accuracy mark here and here, and accuracy marks there. The reason why the accuracy is because your calculator can do it for you. And if you did use your calculator in this case, that's perfectly fine. Let's calculate the coordinates of the stationary points. Now remember, a stationary point is when the derivative, or the gradient, of the tangent is 0. So I need to find the derivative and put it equal to 0. So the derivative of my original function is 3x squared minus 12, and I put that equal to 0. Divide both sides by 3 to make your life easier. Factorize. So I've got two x values. I've got x is -2 or x is 2. Take both of those values and sub them into the original equation, not the derivative, into the original. If you sub x to be -2, you'll get a y value of 32. And if you sub x to be 2, you get a y value of 0, but you should have expected that because it's a repeated x-intercept, meaning it does turn on the axis. These guys here, we just found, are your stationary points. Now we need to find our point of inflection, and many of you did get stuck on this in the exam. The point of inflection is the point where the concavity of the graph changes. So for example, if I've got a graph that looks like this, which is kind of how a graph's going to look, like that. There's a turning point, there's a turning point or stationary point. Now the point of inflection will be that point in the middle where concavity changes. It changes from being concave down to being concave up. And it's directly in between the x coordinates. So if I put in my x coordinates here, the x coordinates are my stationary points, that one's -2, and that one there is 2. So what's directly in between the two of them? Directly in between -2 and 2 is 0. So my point of inflection happens when x is 0. So I take that x value, sub it into the original equation, and I get 16. So I know now that the point 0, 16 is my point of inflection. Now there's actually another way to find a point of inflection, and I'm just going to touch on it now. And we can delve into it a little bit later again. But another way to find the point of inflection is by putting the second derivative equal to 0. So there will always be a point of inflection when the second derivative is equal to 0. So let's do that. We find the derivative of the derivative, which is 6x, put it equal to 0, divide by 6, so x is 0. So that leads us on to sub 0 in, and we get the point 0, 16. So that's just another little way to find a point of inflection, and I probably wrote that on a few of your pages. Great. Now we need to go and actually sketch this function. So let's do that. Sketch the graph showing all important points. Now when you sketch the graph, again, you don't have to be 100% accurate. Just gauge everything roughly okay. So we know that it's got to pass through -4 and 2. as our two turning points. We also know that it starts by being an increasing graph. The way we know that is by the original function. Here we go. That has a positive coefficient, the x cubed. So we know it starts by being increasing. And we know that it's going to have two places where it turns, two stationary points. So let's have a look. Our graph looks like this. It's going to pass through -4. So I'm going to roughly find where -4 is here. Again, you don't have to measure and be exact. And then 2. So I'm actually going to do a rough freehand drawing of this graph first. Sometimes I find it easier to do that. As long as I get my point of inflection axis, it's going to turn on there and carry on going. Again, don't be too sharp. If you're too sharp, you're going to lose marks. Make sure you've marked all your coordinates. That's -4, 0. There's a stationary point, -2, 32. Don't forget about your y-intercept, which in this point, in this case, is also our point of inflection, 0, 16. There's your other repeated x-intercept and your stationary point, 2, 0. It's going to fill in other stuff that we need, x, y, and there's my origin, and f, because that's the name of my graph. Now let's just have a look at mark allocations. Actually, the previous one I didn't do mark allocations for either, so let's start there. First of all, you get a method and an accuracy mark. Just using the right method, getting it accurate. Then you're going to get accuracy, accuracy, and accuracy, accuracy. Right. Now, when you actually draw your graph, this is how we allocate marks. You get a mark for getting the shape right. So if it's way too sharp, you do lose a mark. If it's going in the wrong direction, you get a mark for the y-intercept. You get a mark for the x-intercepts. And you get a mark for your stationary points.